Alright, this is part 2 of incline planes. So let's take a look at this number 2 in our note sheet here. We have a 10 kilogram block that's sliding down a 25-degree incline, and it wants to know the coefficient of kinetic friction between the block and the incline, and it's sliding at a constant velocity. That's kind of critical when we look at our free body diagram. So the first thing I'm going to do is I'm going to draw in some forces that I know. The vertical force here is the weight. And then again, I can break this into components where I have a component of the weight that's pushing into the surface, and the surface is pushing back on the block. So I'm looking at that force here, and we're calling that the normal force. And then a component of this weight is actually causing it to slide down the incline, which I'm just going to label right here, and that's going to be F sub D for the force that's causing it to slide down the incline. Because it's sliding down, I have friction that's sliding, or that's acting upward on it. It's kinetic friction because it is moving. And I also know a couple things. Because it's a constant velocity, that means the acceleration is 0 meters per second squared. That means that the net force is 0 newtons. And if the net force is 0, that means the forces in the direction of motion are equal to the forces opposing motion. And in this case, FD is in the direction of motion and FK is opposing. So therefore FD is equal to FK. So those are some things that I know. I also know a few other things about it. I can find the weight. The weight is equal to mg. I know the normal force is a component of the weight, and this is my right angle. And this angle here is congruent to this angle right up there. So Fn is the adjacent side, so it's going to be the weight times the cosine of theta. Fd, on the other hand, is the opposite side, so it's going to be the weight times sine of theta. And we want to know the coefficient of kinetic friction, so that is Fk over Fn. I'm just going to do some substituting here. If you want to actually solve for each of these, that's fine. There's nothing wrong with that. I'm just showing you that you can use substitution to go through this process. We said here that Fk is equal to Fd, so therefore it's equal to the weight times the sine of theta. And I'm going to substitute right in here. Fk is weight sine theta divided by weight cosine theta. The weights actually cancel, so mu k is equal to the tangent of theta. And if I do this in my calculator, tangent 25, and I get a value of that right there. And because my angle is 3 significant digits, then my answer is going to be 3 significant digits. So I'm going to have 0.466, that value. And again, that's the way through substitution that you would have to show that. Again, you could solve for the weight, solve for the normal force, solve for the kinetic friction, plug those two values in, and you get the same exact answer. Alright, let's look at 3. Alright, see if you can identify what's different between this example and number 2. Hopefully you see this. The block is accelerating. And because the block is accelerating, what does that tell us? It tells us there's a net force. So this time, if we're looking at the forces here, we have a force that's down, which is the weight. We have a force that's pushing up on the block, which is the normal force, and a force down the incline. And we also have kinetic friction, which is up, but how is kinetic friction going to compare to the force down in this case? If you notice, my vector is smaller than this. So therefore, if it's a smaller force, these do not balance, and you have a net force down the incline causing it to accelerate. So that's the primary difference between this one and the other one. So I'm going to see if you can get an equation for net force. Pause the video and then see if you got it right. Alright, so right here I have F net is the forces in the direction of motion minus the forces that are opposing motion. And this is not equal to 0 this time. and we want to solve for the acceleration of the block. So we're going to be solving for the acceleration that's within that net force right there. So let's solve for FD and FK and see if we can solve for the rest of these values. So we'll start off with FK. FK is mu k times Fn. Well, I know mu k, it gives me that value, but I don't know Fn. So I need to solve for Fn. Fn is the same as it's always been. It's going to be the adjacent side of this angle. So it's going to be the weight times the cosine of theta. Well, I don't know what the weight is. The weight is equal to mass times gravitational acceleration. So I can solve for weight, solve for Fn, solve for Fk. Perfect, that takes care of that term. Now I need to solve for Fd. Fd is the opposite side of this. So Fd is going to be the weight times the sine of theta. And I know the weight because I already solved for it here. Sine of theta I can solve for and find Fd. Pause the video, see if you can actually work all this out and find Fk, Fn, weight, and Fd. Okay, here's the work that I went through. Again, I solved for the weight. I used the weight in both solving for Fn and Fd to get those values, and then I used Fn's value to solve for Fk, which is there. Now I have Fd and Fk, which is what I need to find the net force. So that's kind of my next step. The net force is equal to Fd minus Fk. And again, I can use arrows to show those values. Get a net force here. So I've got 220. So I'm going to be subtracting off this value. So I'm going to take 281.05 minus my answer, and I get this value, 60.291. Now if I look, here's where I have an addition subtraction rule. So I'm good to the ones digit, good to the ones digit, and then when I subtract, my answer is only good to the ones digit. So these are not significant here. So I only have two significant digits now. And then what can I solve for once I know the net force? Good. Acceleration is net force over the mass. So it's pretty straightforward at this point to plug in your net force. And your mass is 50.0 kilograms. So 60.291 divided by 50. And I get a value of 1.2 meters per second squared. Again, two significant digits on my answer right there. And let's look at number 4. Last one here of the group. This is a little tougher. Pause the video, read question 4, and then see if you can come up with all of the forces acting on the system. Alright, let's see how you did. If we look at this one, this is the easier part to start with. We know that there's a weight acting down on this. I called it weight 2. And we also have a tension which is pulling up due to that string here. So those are the two forces that are acting on that block. On this block, we have the tension which is pulling up on the block. We have its weight, which is acting straight down. I'm sorry, the tension is pulling up the ramp is what I should say there. The weight is straight down. We have the normal force, which is perpendicular to the surface. We have a force that's causing it to slide down the ramp. But in this case, the block is moving with a constant velocity up the incline. Because it's moving up the incline, friction is acting to oppose its motion. So friction is actually acting down the incline this time because it's sliding up the incline. So you should be able to see those forces there. Now what I want you to do is I want you to solve for the net force on both this first block and this second block. So set up two equations where F net equals based on the direction that this is moving. And just so you're aware of this block, if this is sliding up the ramp, then this has to be moving down. Okay, so swishy's kind of up here, so it's moving that direction. Alright, pause the video and see how you do. Okay, this is what you should have. If we look at the first block, again, the net force, or the forces in the direction of motion, which is just the tension. minus the forces that are opposing motion. So that would be Fk and Fd, so we subtract both of them off of there. Again, we subtract all the forces that are opposing motion. In this case, the direction of motion is weight 2, and opposing motion would be the tension. So those are our two net forces. And what does it say about the block? It says that it's moving at a constant velocity. That's critical. Because it's moving at a constant velocity, we know the net force to then be equal to 0. 0 newtons in both cases. And we also know something about it. The tension in the rope is the tension in the rope. So T in this equation is equal to T in this equation. So what I want you to do now is solve both equations for T, and then we'll continue to reduce down here in just a bit. So solve for T and see what you get. Pause the video. Here's what you should get. Tension is equal to Fd plus Fk, and tension equals weight 2. That's it. We are trying to solve for the coefficient of kinetic friction, which would then be in this term right here. So I'm going to do a little bit of algebra to solve for Fk. Since these tensions are equal, I'm going to set these equal to each other. So weight 2 equals Fd plus Fk. Again, just setting these two equal to each other. And now I'm going to solve for Fk. So Fk is equal to weight 2 minus Fd. What does Fk equal to? Well, Fk equals mu k times Fn. So I'm going to substitute mu k Fn for this. This equals weight 2 minus Fd. And now I'm going to substitute in for Fn. Well, actually I'm not. I'm going to solve in this case just for Fn and Fd for you. So we'll do that stuff over on the side. Try it on your own. Again, pause the video. See if you can solve for Fn, weight 2, and Fd. And then we'll solve for mu k using those values. Again, I'm going to do it just right over here in this space. Pause the video. Come back in a second. Okay, here's what I got when I solved for each of those values. So you can take a look, give you a second to look over those items. Solve for weight 2 right here, it's mass times g. So I found weight 2 is 196 newtons. And then Fd and Fn are all pertaining to the weight 1. So I need weight 1 is mass times g for that particular weight. So I have mass times g times this, and mass times g times cosine of 40. So here's my Fd and my Fn values and my weight 2 values. So from those three values, I can now solve for mu k. So algebra-wise, mu k would then be weight 2 minus Fd all over Fn. And then I can solve for that. Mu k is equal to 196.00 newtons minus Fd, 157.48 newtons, divided by 187.68 newtons. Again, I have an addition subtraction rule right there. So I'm going to take 196 minus 157.48, 38.52. Good to the ones, good to the ones, answer's good to the ones. Divide by this value still. So my mu k value is now this value right here in my calculator, which rounds to 2 digits, so it'd be 0.21 for my coefficient of kinetic friction on that. So hopefully that helps. Again, the key to these problems is making sure you have a good diagram with all of your forces on it. Make sure that you set up what are your net forces. If you're accelerating, then it's not going to be equal to 0. The net force will be equal to the mass of the system times the acceleration of this system. Remember, they're accelerating together. So the mass would be the total mass that's accelerating. But again, it's really, this is kind of the critical step right in here, is getting all of your diagrams set up and then getting your equations pulled from that diagram. Again, hopefully that helps. We will finish going over the rest of those problems tomorrow. So hopefully you can use this as a guide to get you to that point.